Hi, Fida. Hope you can hear me. I'll wait for a couple more minutes before I start. So, if somebody else wants to do it. Okay, I'll start. Uh, so this week, we will cover the topic bulk queues and Erlangian queues. That was the content of week 6. And yeah, so and then we'll solve some problems related to that. Okay. So firstly, what do we mean by bulk queues? By bulk queues, we mean that when we are kind of either we are having bulk arrivals, that is packets are arriving in groups of uh, in chunks instead of a single packet at a time. Or the other variant is when you can have bulk service where you perform the service procedure in batches, either full batch or partial batch, instead of doing it one at a time. And so a lot of sophisticated kind of mathematical techniques are required and to solve these kind of things. And this was, this was a new topic for me as well. So I had to go through the lectures myself. And I made some short notes, which I'll share along with the drive. It will be uploaded on the drive link after the class. So yeah, it might help because you might need a set of formulae handy to solve problems. So that's one set, and then we'll move on to what's known as Erlangian queues. So for which we are introduced to the Erlang distribution. And my bad, this should be T. So in the Erlang distribution, it is essentially the sum of KIID exponential random variables, and the and the beauty of this distribution is that if k is equal to 1, this behaves exactly as an exponential random variable. While if we take k approaching infinity, it becomes a deterministic process with the mean with the exact value 1 by mu. So we can model a wide variety of different kinds of service distributions and arrival processes using the Erlangian k distribution, right? And then we have the general phase-time distribution, where um, we try to model queues using an initial state and a transition matrix. So uh, these are continuous time Markov chains, and we try to model it by kind of an amplitude and a phase. So this is another topic that has been studied in this week. So as I said, I put some short notes here and there. And then, we generalize our MM1 queues into MEK1 queues and the EKM1 queues. So, and then, so if you remove the Poisson distribution at either end and make it into an Erlang K distribution, and then you can, and as it follows, we can draw parallels between what we have between the Erlang K queues and what we have studied earlier. So those parallels can be exploited. So we can draw parallels with bulk service and bulk arrival. Yeah. I think Siddharth dropped. Hi Siddharth, welcome back. I literally enjoy it. Hello, can you hear me? Siddharth, do confirm. Not. Okay, no response. Wait for a minute, otherwise I will continue. Okay. This will be recorded on YouTube, so hopefully you'll be able to see it. Okay. So based on this basic theory, and I'm not going to repeat the theory because it's really a lot of mathematical details, and there's no way I can kind of finish it. And so I would highly recommend you to go over it yourself. But okay, if that dropped off, let me wait for a couple minutes. Hi, can you hear me, Fida?
Yes, sir, I can hear you, but my network is unstable.
Yeah, I got it. Okay, I'll continue. You can if
Is
you
it
disappear.
available in the YouTube, sir?
Yeah, we will make it available, right? I upload it every day once I'm done. So
Okay,
yeah, it will be available. But yeah, I will continue then. Fine.
thank you.
Thank you. Let's yeah. So let's solve the first problem. So problem number one that we did. So we have a system where there is like a single server. 1 second. I'll just So yeah, so let's say we have a single server, one server in a queue, and and so and then the customer, and then there are customers who arrive in groups, right? In groups. So this is kind of, you can see, a bulk arrival kind of system, and each group, um, so it arrives in, let's say, at a certain Poisson process. Poisson process, something like, let's say, 5 groups per hour, right? And so you have probability. Uh, so you have probability, let's say, P equal to 1/4, that the number of like, let's say, number of people in the group is maybe 2, and you have probability 3/4, and I'm doing it as P1 minus P deliberately because you have only 2 possibilities, let's say. And you have probability 3/4 that the number of members in your group is, let's say, 10. I'm just randomly picking numbers. And for all customers, the service time is exponential with mean 6 minutes, right? So mean of so service time is exponential, which means the service rate, we know service rate is Poisson, and so 1 by mu equal to 6, which means mu is equal to 1/6 per minute, right? So service time is 6 minutes. Yeah, I'm picking, let's actually pick 5. I think the math will work out better. So let's say service time is exponential with mean 5 minutes. So service rate is 1/5. So you want to figure out what is the average, what is this value, right? You want to figure out what is LQ, which is, as per the normal notation used in the course, it's average number waiting in queue, average number of customers waiting in the queue. How do you solve this kind of a problem? Right? So the first thing we need to identify here is that this is, again, like this is a queue of the type bulk arrival. So it's mx m1, and then so x is we don't know exactly how many customers are arriving, but then we know the distribution, right? So we can say that the expected value of x here is 1/4 times 2 plus 3/4 times 10, right? So this is 1/2 plus 15/2, I think. Yeah. Or like 32/4. So that's actually 8. Nice number. And another thing that we need to figure out is expectation x square and 1/4. So that will be 1/4 times 2 square plus 3/4 times 10 square. And this will come out to be 304 divided by 4. So that's 76, I believe. Yeah, that's 76. I might be making mistakes because I'm just cooking up these numbers. So then we have these statistics and we know the values of lambda and mu. So this is lambda. Lambda equal to 5 groups per hour, and mu is 1/5, 1/5 per minute. Or if I have to convert for, and this is one thing we should be careful about, that when we are computing everything, we have to keep things in the same unit, right? So if I have lambda in units of per hour, I need to keep mu2 in units, mu as well in units of per hour. So let's say, so I knew that 1 by mu is 5 minutes, right? So 5 minutes is also equal to 5 divided by 60 hours. So then mu will be essentially 60/5. So that's 12 per hour, right? This is the value of mu we'll be working with. We need to keep them in the same units. And so very clearly, so we have these quantities that we define as R is lambda by mu. So that is nothing but 5/12. And we have rho, which is lambda by mu times expectation of x, right? So that is 5/12 times 8. That's just, yeah, 2, 3. So it's 10/3, I believe. So, and so from these, we can actually calculate just using the formulae. So you can essentially pick the list of formulae from my notes here or refer back to the lectures. And it's really a tedious job to derive all of these again from scratch. So I won't do that. And yeah, it's not suited for an exam situation either. So then we have the total number of customers waiting, that is rho plus r times a to the power x squared by 2 times 1 minus rho. And I don't really know the answer to this because I haven't calculated. I mean, yeah, you can just plug in the values that have been obtained here. So this is rho, this is r, this is exponential value of x squared. So just plug in, you'll get the value of L. And then LQ will be nothing but L minus rho. And then that's the number you need the average number of customers waiting for the queue. Right? So that is there. So this is a case where lambda and mu were known. I just want to make a note of this, right? So this was just based on formulae. Hope it is clear. And then in the second problem, we will try to solve a problem of an MX M1 queuing system and parameters, but here lambda and mu are unknown. So we just regard them as some parameters. Some parameters, right? And so now you want to obtain the value of L, which is expected number of customers in all. So both in the queue and waiting to be admitted in the queue. Expected number of customers in the system. And you want to obtain it in terms of like lambda, mu, and rho, which is lambda, right? So for this, and the only information you'll be provided is, let's say, I mean, you'll be provided the nature of X here. So you're told that like whenever there is an arrival, at arrival time, you have probability 0.5 that number of customers entering will be, let's say, 1. That's 0.3, and probability 0.7 that the number of customers entering is actually 3. Right? That's it. Something like that. And whatever, it doesn't really matter. The concept is the same. So probability is 0.3 that there'll be 7 customers entering at a time, and probability is 0.7 that there'll be 3 customers entering at a time. And so you really want to write a formula for it, right? And so what we really need to find out is 2 quantities again. Expectation of X, which is 0.3 times 7 plus 0.7 times 3, which I believe will be 2.1 plus 2.1, 4.2. And then we have expectation of X squared, which is 0.3 times 7 squared plus 0.7 times 3 squared. So this should be 6.3 plus 14.7, I think. Yeah, 14.7 plus 6.3, that should give 21. Yeah, I may be wrong with the calculations, it's the usual caveat. But once we have this, then we can, of course, we can calculate rho in terms of lambda by mu, which is lambda by mu times expectation X, which is, I'll just write to the formula again, it is 4.2 lambda by mu. And then we have the formula for L as R, and we also have this quantity R, right? L equal to R times expectation of X plus, if I just fix the notation here, expectation of X squared divided by to 1 minus rho. Or actually, like if you observe expectation of x, this is actually rho plus r expectation of x squared by 2 minus rho, where r is nothing but lambda by mu. So this becomes equal to lambda by mu times 4.2 plus 21, I think. Yeah. Because rho is lambda by mu times 21 time divided by 2 times 1 minus 4.2 lambda by mu. So you can calculate this. So, and then you might essentially have a multiple choice question where you can have multiple correct options. So one of the options can look like 25.2 lambda by mu by, or like, if you do the division, 12.6 lambda by mu divided by 1 minus 4.2 lambda by mu. This could be one of the options, or you can have various permutations of it, which will involve rho and then r, where r is lambda by mu. So you can have rho figuring in the expression, r figuring in the expression, but you essentially can do the algebra and see which of the options match. Really. So then you can solve for these kind of questions. Okay. Okay. And let's has dropped off and wait for a couple minutes till she joins. Okay, let's resume. So let's do a short question, or more like a conceptual question, that so in, let's say we have something like MK M1 system. So we have bulk arrivals, and with parameters lambda and mu, and the number of, and let's say k is equal to 1. K is equal to 1. So can we say that the number of people waiting in the queue, LQ, is lambda by mu times the total number of people in the queue? So the answer for this is actually yes, because what, with k equal to 1, this is effectively becomes an MM1 queue. And we know that this property holds for an MM1 queue because the blocking probability rho for an MM1 queue is nothing but lambda by mu. And so then LQ is, so the LQ comes to be the probability that you actually have the line busy. And so you have lambda by mu times the probability that there are packets in the queue and you have a head of line blockage. So then that's what, so you immediately get this result. This is from MM1 queue. So sometimes you can get this kind of a question where you are essentially, you will have to reflect on properties of MM1 queues. Yeah, so simple relatively. And okay. So this will kind of be a problem on phase queue distributions. And even for phase queues, the theory is really involved and it requires a lot of algebra. But what I would suggest is go through the lectures and prepare notes of the common types of queues that have been covered in the lecture, and most likely you will be able to reuse the same formulae, the same expressions directly to solve your questions, because the lectures do cover a lot. And okay. So you have a two-stage facility, and so then you have stage one. So any person coming in or any, let's say some kind of a factory automation system, or let's say coffee bean processing factory, whatever. But we have something coming in, and then it passes through two stages, stage one and stage two. And so after it passes through stage one, it has two options really. It can optionally go to a stage two, and or it can just directly go to the exit. So then the probability, so then like, let's say at each of these places, so you have exponential with parameter mu1, and then the service time here is again actually 1 by mu1, and the service time here is again exponential with mean 1 by mu2, right? So then the service rates are then correspondingly Poisson with mean mu1, we know that. And so there is a probability P that the products that will come out here will be sent to a stage two, and there is a probability 1 minus P that it will actually send straight to the exit. So it will exit the processing stage. And so how do you really model this kind of a system for, so then if you have to model this as a phase type distribution, PH initial state alpha and Q tilde, where Q tilde is kind of the, so if we go back to the discussion in the lectures. So if you write the continuous time Markov chain matrix, the kind of rate matrix is Q, and you divide it into these four parts, Q tilde minus Q tilde times the eigenvectors E, 0 and 0, then if you write it in this form, then what we really need is this Q tilde. Because once we have this, we can define the whole matrix. And so for this kind of a system, you have been asked to find out what is Q tilde, right? And so then as I've drawn, this is like a continuous type Markov chain with 3 states, right? So you have this object coming in, stage 1, you can, and then 2, and then 3, right? And then you can write this as third state as an absorbing state. Because you're not getting out of the exit state. Once you are here, you're here. So then the arrival rate here is lambda, right? So the arrival rate here is lambda, and or whatever, it doesn't really matter. So essentially, you have a rate mu1, or actually p times mu1 of going into state 2, and you have another transition 1 minus p times mu1 of going straight to the exit, right? And then, and over here, the transition rate from 2 to the exit is this mu2. And the reason, so you had a net service rate of mu1, which gets split into 2 probabilities, right? Because of the probability p and 1 minus p, that it can have 2 possible different transitions. Okay. So then, so you really want to figure out the transition matrix for the non-absorbing states here. So the non-absorbing states are 1 and 2. And so the Q tilde here will be from 1, the exit rate is minus mu1, and you have like, so, you know, then, so you have actually 1 second. So from 1, so obviously you'll have minus mu1. The complete Q matrix will be minus mu1, p mu1, 1 minus p times mu1. And then for 2, you'll have minus mu2. Actually, here minus mu2. Nothing really from 1 to 2. Nothing from 2 to 1, and from 2 to 3, it's mu2. And from 3, it is 1 minus p times mu1. Coming in from, yeah. We'll populate this later. So from, there's nothing from 3 to 1 actually. And everything gets absorbed here. So it's 0. So that's how you write it for the absorbing states. And so if you divide it into 0, 0, this will be Q tilde, and then this will be minus Q tilde times E. So from here, you have the non-absorbing states matrix as Q tilde equal to minus mu1, P mu1 0 minus mu2, right? And so this is one aspect. And then you want to also figure out the expected value of service time, right? Expected value of service time. One way of doing it can be to go to hypoexponential distribution, hypoexponentials, and solve. And that of course is solving Kolmogorov equations and getting the solution. So that kind of approach is taught in detail in the lecture. It's cumbersome. But then the second approach is to really identify that we can have two cases here, right? We have t distributed as exponential of, we have two processes, x1, which is distributed as exponential with 1 by mu1, and then x2, which is distributed as exponential with mean 1 by mu2. And so we have t equal to x1 with probability p, actually 1 minus p, because 1 minus p is the probability that it will go straight to the exit, and it will be x1 plus x2 with the probability of p, because then it will pass through the two states. So then t, like the PDF of t as a function of t, this will actually be 1 minus p times an exponential random variable with mean 1 by mu1. So that is nothing but mu1 times a to the first minus mu1 t plus p times x1 plus x2, which is a hypoexponential. And and then from the lecture we can just substitute the formula for the hypoexponential, and we have our solution here. So not going into the derivation of the hypoexponential, it's there in the lectures and it can be covered, but yeah, that is kind of the approach that needs to be taken to identify that there are two cases here. One where it's a normal exponential, the other where it's a hypoexponential, and then just to kind of plug in the distributions, because you will have probability 1 minus p that it will be the exponential, and probability p that it will be the hypoexponential. So this is really the PDF of. And so from here, you can compute anything. If you are asked to compute the mean processing time, you can compute expectation of t or variance and whatever. It's just computation. Yeah. So then another problem. So now we'll discuss the Erlangian queues, and so we'll do a couple problems with that. So firstly, firstly, a kind of a simple conceptual problem that, let's say we have a sequence of queues with Erlang arrivals, right? So we have one queue which is EKM1, another queue with EKM1. And we have kind of arranged them in a sequence. And let's say hypothetically, we have infinite such queues. We have infinite such queues, right? So question is, what will this entire system behave like? And the answer is really DM1Q, because as we know that if we sum up these Erlangian random variables, like sum of some random variable which is sorted k, if we take k to infinity, then this essentially approaches a deterministic random variable, and so we'll end up having a DM1Q. And it's deterministic random variable which is equal to the mean of the Erlangian distribution. That will just kind of converge at the mean. So that is kind of one conceptual theoretical idea. And then let's say, so when the problem, so now we have, let's say we have kind of a factory, and in the factory there are machines, and machines firstly we have one repairman in a factory, and whose job is to service faulty machines, right? So faulty machines, and machines become faulty, something like, let's say we call it as fault rate 2 per hour, right? 2 per hour. And so, and then the service, the repairing process has let's make it 5 per hour. The repairing process has, let's say, 2 steps, and so in sequence, 2 steps in sequence, and each of the steps has mean. It's like each of the steps is exponential with mean as like with a mean of 5 minutes, with a mean of 20 minutes, let's say, right? Or 10 minutes. So then we have mu. So we'll model this later. So then we can model this as a queuing system, right? What we want to find is average idle time for a machine. So that is average time that between the point where it breaks down and the point where it is functional again, right? So the average waiting, like average idle time. So we can model this as an MEK1 queue, right? Where so this is a queue of faulty machines. So in this queue, we have arrivals at the rate of 5 per hour, right? We have arrivals at the rate of 5 per hour. Let's actually make this 20 minutes. We have arrivals at the rate of 5 per hour because the machines become faulty at the rate of 5 per hour. And we have, obviously, as mentioned, we have one repairman, so just one. And then we have service at the rate of, again, 5 per hour, right? Because 1 by mu is 20 minutes, which means, sorry. So then, actually, no, this can run into problems. Let's keep it to 10 minutes. So then mu is nothing but 6 per hour, right? Because 10 minutes is 1 by 6 hours, so it's 6 per hour, right? And so, and the value of, and here k is equal to 2 because we have two processes, one after the other, right? And we can define rho as lambda by mu here. So it is 5 by 6, right? And so the waiting time in the queue for this kind of a system, and you can just check the formula by yourself, is precisely this. I'm not going into the derivations again. And you can calculate this, and this will come out to be 1 plus half 3 by 2, 3 by 4 times rho 5 by 6 by mu, which is 6 times 1 minus rho, which is 1 by 6. This actually turned out to be a simple calculation. So it is nothing but 3, I believe it's 5 by 8. Yeah. And so that's a waiting time in the queue, which means the actual waiting time is WQ plus 1 by mu. So that is what? Just 5 by 8 plus 1 by 6. So 15 by 24 plus 4 by 12. So 19 by 24 hours. And so you can convert it into minutes, right? So that will be like, I believe 9.5 minutes. So this should be 9.5 minutes. Not sure of the numbers, you can check the calculation, but this is how you'll solve this kind of a problem, by identifying that this is a set. This is kind of a problem where you can fit the idea of an Erlang K service distribution, because you have a sequence of exponential services happening one after the other, right? So then that is with exponential service. And now we'll have exponential arrivals. So again, we have a queuing system with one server, and inter-arrival times, arrivals, and you are told that this next type of problem, you are explicitly told that arrivals are of the form Erlang type, Erlang type 2, let's say, Erlang 2 distribution, and the mean inter-arrival time, which is nothing but 1 by lambda, is equal to 10 minutes, right? So we know if interval time is Erlang type 2, then the process kind of. So we can take lambda as 1 by 10 per minute. Per minute, or if you have to convert to hours, so it's 6 per hour, right? 10 minutes is 1 by 60, so 6 per hour. And then service times are IID exponential with mean, let's say means 5 minutes. So which means that 1 by mu is equal to 5 minutes, and mu is equal to 12 per hour, I believe. Yep, this is 12 per hour. So then, and from Erlang K, so we are using the formula for Erlang K distribution, and here obviously you are told that it's Erlang 2, so it's K equal to 2. And you want to find the probability that there are, like, there is maybe one customer. There's just one customer in the system in steady state. Or in other words, this is like using the notation of Erlang C, it will be something like P1C, right? This is something that you want to find out. So we know that we have the values here, and we know that for Erlang K, because this is the, again, this is the queuing model that we are analyzing. And again, I'm kind of, again, there's no point going over the details because they are in the lecture. But the probabilities P and C are given for this queuing system are given by rho times 1 minus R naught to the power K, R naught to the power K whole to the power N minus 1, where rho is nothing but, so rho is nothing but lambda by mu. So this will be 6 by 12, which is half. And R naught, it belongs to the open interval 0 to 1, and it is the positive root of the characteristic equation which you solve. Characteristic equation, right? And the equation is given by mu times R to the power K plus 1 minus K lambda plus mu times R plus K lambda equal to 0. So essentially you solve this to get R naught. And so let's put in the values here. We know K is equal to 2, so it's a cubic polynomial. So we'll have, and mu is equal to 12 per hour. So we'll have 12 R cube minus K is 2, lambda is 6 per hour. So it is 2 times 6, which is 12, plus 12 again. So it's 24 R plus K times lambda, which is again 12, equal to 0. So if you take 12 common, so you have R cube minus 2R plus 1 equal to 0. And so this needs to be solved, right? This. So then we can use factorization skills to solve this. So, or you can just use your calculator. I'm just attempting a factorization approach. So you take r square, it's common from here, times r minus 1 plus r minus 1 squared. And so again, we just made up the number, so I don't know what should be the right answer, but so we can clearly see that this is what, yeah, this is what we get. And clearly one of the roots of this equation is r equal to 1, which we reject because we need roots between 0 and 1. We cannot have the common ratio equal to 1. And or we'll have to solve for r squared plus r minus 1 equal to 0, which means r is equal to minus b plus minus root over b square minus 4ac by 2 times a. Right, this is the Sridharacharya formula, and this will be minus 1 plus minus root over 5 by 2. And so this clearly has two values, right? You'll have minus 1 minus root 5 by 2 and minus 1 plus root 5 by 2. And so we'll reject this and accept this because we need r to be positive and r has to be between 0 and 1. Okay. So then we have r naught is equal to minus 1 plus root 5 by 2. You can check this value has to be less than 1. Right? And so yes, once we have r naught, what we have been asked that the probability of 1 cluster in the system. So P1C is nothing but rho times 1 minus r naught to the power k, r naught to the power k whole to the power n minus 1. So n is equal to 1 here. So this will be 1 minus 1. This won't play a role. So rho is, as we have computed, rho is half. So this will be half times 1 minus 1 plus root 5 upon 2 whole squared. Whatever this value is can be computed. But yeah, because as we know, k is 2. This has been told that this is an Erlangian 2 kind of system. Compute this value. It's just by and large, this is a very mechanical kind of question to solve. And yeah, so when we ask any variation of this, and you should kind of know how to solve for characteristic equations for an Erlangian KQ system. So that's all I had for today, actually. And so this is the content of week 6. And in the next week, we'll have further generalized queuing systems, but those are actually like simpler to understand. And there are a wide variety of problems for that. So this is it. I'll stop here. And if you have any further questions, I'll be happy to answer.
Hi,
Yeah.
sir. In question
Hi.
4, what's the diagonal? How is the minus mu1 minus mu2 coming? Can you please explain that once again?
Okay, so this is from the continuous time Markov chain theory, right? That the diagonal elements QII, the diagonal elements are always written as sum of QIJ for J not equal to I. So if you go back and revise, then you'll see that, so that is how continuous time Markov chain evolves. So So you first actually write down the values of Qij, which is more intuitive, which you can directly see from the state transition diagram. And then you fill in the Qii, which will just be the negative sum of the Qijs. And that is how these state diagrams are defined actually, because you need the sum of each of these rows to be zero for it. Okay.
Okay. Thank you, sir.
Yeah. So obviously the others are understood, right? That from 1 to 2, the transition rate is P mu1, P times mu1. From 1 to 3, it's 1 minus P times mu1. If you add them, you get mu1, which is, and then you just write minus mu1. Same for the other two. Okay.
Thank you, sir.
Okay. Yeah, if you have
Sir,
any.
where can we find these notes?
These notes I continuously upload after every class. I upload it to the Google Drive link that I've shared. So you should, I believe the NPTEL team should have shared with you, like along with the link for my lecture. It should have also shared with you the Drive link. You should check with the NPTEL team because I'm doing my part. I've been told to maintain a Drive link. I can even kind of.
Yeah, okay.
Yeah, so
Thank you, sir.
I am maintaining a Drive link, and I've shared the Drive link with the NPTEL team, where I'm
Okay.
uploading these notes from the recordings and from the class recordings, and in occasionally if I'm using some other supplementary material, I'm uploading that too. So it is all there in the Drive link, and yeah, it's. I
Okay.
hope they are sharing it with you. Yeah.
Okay, okay. I got it. Thank you, sir.
Okay.